I'd like to welcome you all here tonight. Tonight is our first Pinhead Town Talk lecture for 2008. It's our 6th annual year, although the Telluride Science Research Center, of which I'm the executive director, has been holding science talks in Telluride for about 20 years. It just so happened nobody knew about them. So we brought them out of the closet and into the daylight or evening about 6 years ago, and we're very, very happy to see so many people here. I do want to apologize for scheduling this on the night of the caucus at exactly the time that the caucus is running. I'm not anti-democratic, and I really didn't mean to mess up anybody's evening. But Ivan's in town. He's in town with a group of chemists and other physicists who are here with the Telluride Science Research Center workshop. It's the third winter workshop we've ever held. We normally have these workshops in the summer, but we're branching out into the winter. So we're very happy they're all here. It was really tough to get here, but they're happy now with the snow. I do need to thank the Telluride Mountain Village Homeowners Association, who, along with the donations that you guys so generously give us, really underwrites this program. And I have to thank TSRC and Ivan for coming out today. So Ivan Schuler is a very unusual scientist. He is a physicist, a professor at University of California in San Diego. Did I get that right? And but he's also a playwright and a producer, a writer, a comedian, and an avid believer in the importance of science communications. So, without further ado, thank you very much for coming, and let's welcome him to the talk when things.
Okay, I'm very happy to be here. Took me a while to get here, well, the first thing I have to do is everybody that looks at the pinheads always has an image of what a pinhead should look like. And what I want, the first thing they always imagine is a guy with a tie and a jacket. I'm very uncomfortable with this jacket, and many of my people that know me, so I'm going to take my jacket off if you forgive me. So, okay, so, no, the other thing is I'm going to make this a little bit more of a participatory kind of a talk, so I'll need your help at some crucial moments. But the first thing that I want to tell you is this: I make movies, and sometimes people appear in my movies, and so I'll take a picture of this audience. Usually the pictures, you see them from there. I have a lot of pictures from here. So smile. There is another reason why I'm taking this picture. And this is for my colleagues, because it turns out that many of my colleagues come and say, I was at your talk. I know if you were here at my talk. Okay. Now, you may wonder what is this guy doing with all those measurement tools. Actually, this turns out that UCSD has a library called the Geisel Library. The Geisel Library, Geisel was the man who invented Dr. Seuss. And Dr. Seuss, actually, before he was drawing Dr. Seuss, I found in the basement of a relative who died, this book, and Dr. Seuss used to make other drawings, and this is a drawing of this that Dr. Seuss or Geisel made, and this is a guy with a bunch of measuring devices, and that's what we actually do, we physicists do, is we do measurements on things, and that's sort of what I will show you more or less here in this, during this talk. Now, when you get to my stage, what happens is suddenly about 3 months ago, I got a bunch of people sending me this, and it said here, it was the scientific achievement of the year, the smallest bananas ever created. And it established Dr. Schuler, you see that's how I look like, as the world's leading authority on nanotechnology. All right? This is not a joke. This was in many newspapers. You may find, I don't know this person, but I don't know how they got to this, but somehow. Okay, so, okay. So this is the impression that most people have about what we do, and then I want to kind of try to dispel that we are not quite like that. So don't believe every preconceived notion that you have about everything, because many of the preconceived notions, I was just talking to a gentleman outside there, and he was asking me some questions, and my point is that many of the preconceived notions that you have may be wrong. They may be completely wrong, and they're so wrong that, for instance, at this moment, even my colleagues here, with one exception, I must confess, you're assuming that I have glasses on, and I really don't, you see. Okay? So there's a preconceived notions that you develop as the time goes on, and then you let those preconceived notions that you have is to guide you into your thinking. And so what I want to do is dispel that notion and show you some very unusual things and some very interesting things, and perhaps something that if you walk away from here thinking the following, that science is kind of interesting. There's these nuts out there that are interested in it for some reason, but it's not like we believe it is, and sometimes it's useful. Well, I should say, not all science is useful. Some science is useful. The problem is this: the technological revolution arises from basic research. What we do is we make a question and we give an answer. The problem is that it's very difficult to know which of the questions give an answer that becomes useful. So many times with scientists, there is this confusion that there is between technology and science, and many times with scientists are asked the question, so what is this good for? Well, the problem is that we cannot answer that question very easily. So it is impossible to predict which will give results. And I'll confess here to you. We cannot, if I had known which research will give that result that will create the next Microsoft, believe me, I know where I would invest my money. But I am probably as good or probably worse than most of you, since probably some of you have houses here in Telluride. And I'm probably, I have not invested my money so wisely as you have done it. But the reason for that is this, is because it's impossible to predict which of these scientific things that we do give results that become useful, that become interesting to you, that they turn on the lights, they make this microphone work, whatever. So, but one thing I can assure you, this I can assure you 100%, you can, if somebody wants to take a bet on this, I'll bet on this one, that the totality of the science, all the science together somehow produces results. Now this is a concept that I want you to walk away from. That's it. If you walk away with this, I am happy. The rest of it is just trying to support this. Okay, now the other thing that I want to tell you is this, that many of the physics that I will show is like magic. It is not magic, but it is like magic. And the reason it's like magic is because you're accustomed to thinking in a certain way. Now, let me just show you here, for instance. It's like magic like this. So this is Harry Potter. See, there is a magician. There is the... Now, I'm not... see, this guy, the magician has a beard. I have a beard. You see, so I'm kind of like a magician, okay? See, Harry Potter can fly on that broom. Now, I almost flew quite comfortably on that broom to here. You know, there were some problems with the broom, and it didn't fly at the end, but, you know, the broom I flew into, at least up to Denver, was much more comfortable than Harry Potter is having in there. See this? He has a stick there with the light on it. I have a stick with the green light. I have a stick with the, you know, all kind of colors. I have real light, you know. I have red lights. I have all kind of lights, okay? So physics is like magic. But it has another thing that physics is. That science is better than magic because it's real. It's not just some things that is imagined, it's real. So although it seems magical, it is real. And I'll show you examples of that in a second. And this is another thing that I want to end up getting you to live. It's not that we believe that quantum mechanics, for instance, which is something that I will talk about, is real or it exists. It's not that we believe that evolution exists. How many people believe in evolution? Can I have a raise of hand? How many people don't believe in evolution? Okay, all you guys are wrong. All you guys are wrong. Because we don't believe in evolution. Evolution is a scientific theory that either is correct or is not correct. We prove it scientifically. It may be there or it may not be there. And if as soon as this gets disproven, we the scientists will be the first one to throw it out. But there is certain methodology by which we prove that something is correct and something is not correct. So saying that who believes in evolution is already, the question is loaded. And it's the wrong question to ask. Okay? Now let me just give you an example. How can I'm a physicist. So how can I not put up some equations? So here it is in equations. So this is what I'm going to explain to you, all these equations. These are called the Maxwell's equations. Okay, so these will give rise to all classical physics, or electricity and magnetism, which is the course I teach. Now I will show you something that has to do only with that minus sign there. See that minus sign? You might think, well, this is something, you know, that scientists do. Look at that minus sign. I'll show you a magic with that minus sign. This is magic. This is real. So I will need some helpers for this. So I will need, okay, good, come up. That's very good, a helper like this. Okay, wait a second. Just, you come up, hold my hand. Okay, come up here. You sit down. I need another helper. Somebody actually tall, or semi-tall. Oh, yeah. Well, if you look, let me put it this way. I teach, so if you guys don't come, a volunteer doesn't come up, I'll just take one. Okay, good, good. This guy looks like a skier. Maybe you can give. Okay, so you come here, stand next to him. Okay, so what you're going to do is you're going to hold on. Okay, just first vouch for me that this is just a copper tube. Right? It's just a tube. There's nothing, okay? And you also vouch for me, right, that this thing here, these are 2 plugs that I have, right? And they are of the same size, right? I have 2 plugs here of the same size. So double check this, right? 2 plugs, same size. What's your name? Andrew. Okay, so Andrew has 2 plugs of the same size. And you can vouch also that they kind of go in here loosely, right? They're kind of loosely going there, right? Loosely going there, right? They're very loose. And try to see if it sticks to this tube. Try to see if it sticks to it. Don't drop it, but try to see if it kind of sticks. Put it on top. If it's magnetic or something. Yeah, it doesn't stick, right? It doesn't stick to it, right? Okay, now we're going to do an experiment. I swear to God, I do this experiment every year that I teach, and every year I'm wondering, something is going to go wrong. But science is not like nothing goes wrong with this experiment. You hold on to the tube. You hold it like this in the middle there, okay? And I'll give you this, and you will drop it in. I'll catch it at the bottom. You'll drop, no, just show it to them wait, hold it like that, you see, so that they can see it. So hold it like that, you drop it in, watch when you drop it in the holder, and watch when he drops it in, I'll catch it. Could you see it coming through again? Let's do it again. Raise it higher, Andrew, so that people can see it. Okay, so I'll catch it here, drop it in, goes in, okay? Now I'll take the other plug, same size, exactly same size. Drop it in. Now drop it in, I'll catch it. You broke my experiment, man. Wait, what did you do to this? It doesn't come out. Something is wrong. You see? You see that? Let's do this experiment again. Drop it in there. Watch that. It takes forever to fall to that tube. Forever. No, don't shake it, don't shake it. Just leave it like that. It's going to come out. There it came out. The only difference between these 2 tubes, between these 2 plugs, is that they are different materials. Thank you, thank you. An applause here for Andrew. And your name is what? What? Dennis. Okay? The only difference between those 2 is they're different materials. One is a material called aluminum, or aluminium if you're English educated, and the other one is iron. Now, you may think, what the hell is all this? I always wondered what is this thing for, why people wear this. They tell me it's to keep the tie on, to keep the microphone on, so I'm going to take my tie off. Okay? All right, so now you always wonder what are those 2 plugs made out of, and why are they so different? And they are really different. I mean, I can just, so that you don't believe there is some trickery here, I put that plug in there, and it takes forever to fall through. It just takes forever. Watch it. It's just going to fall through. I'm 100% sure. Maxwell's equations, minus sign. Okay? It falls through always. But I'm always amazed. And the only thing is the difference between those 2. And that difference has to do with what was the biggest invention of the 19th century, I believe. Now, you guys don't have anywhere, a periodic table here. So we scientists always carry the periodic table with us. So I have a periodic table, so I'm going to take this is the striptease part of the show. Okay, so this is this thing is called the periodic table. Okay? And you see here in the periodic table are those elements. Okay, there, you see? That's the periodic table. The biggest invention of the 19th century. I'll continue like this if you guys stay here long enough. Okay. All right, so that's it. So, and it's the only difference between those 2 things is one is a material somewhere around here, and another one is a material somewhere around here in this periodic table. Can you hear me right? Is this okay now? No, yeah, it's okay. The where I press the microphone. Okay. Okay, so that's what I showed you is the magic that is contained in that minus sign. Now the reason that this is so magical is because we scientists can see in those equations things that those of you that are not scientists cannot see. Well, in fact, we physicists can see in those things, I should say. Most of the people here are chemists. They can see this thing. Okay, so I have to insult everybody at some level. Okay. Why is that? Because this is like this book, The Little Prince. I don't know if most of you read it. This book is very profound. It's philosophically very profound. My wife gave it to me when I was 24 years old, so I could really understand this book. And see, the Little Prince was going around the world and asking, how do adults think? And so he was showing them this picture. And they was going around and showing that the adults this picture and saying to them, what is this? How many of you guys have read The Little Prince? Have you read it? So most of you know what the story here is, but they were showing them these pictures, and most adults would look at that picture and they say, that's a Mexican hat. And the Little Prince got very disappointed because he knew that behind that drawing there was something else. There was a boa that swallowed an elephant. But they could not see this. The Little Prince could see this. That's how those equations are. We see behind those equations things that perhaps you don't see, and we think that's very boring. It's not boring. This is very interesting, this boa with the elephant. Those equations are very interesting, like I showed you. And there is many, many more interesting things besides those minus signs that I showed you. So that's why. So you see, from the relationship between these magnets and electrical charges, things like applications came out totally unexpectedly, like electricity, which changes our environment. We can sit here very comfortably in a t-shirt. You couldn't have this without this. And this came out of asking these questions. How do magnets and electric currents interact? So what this allows us is to extend our bodies. Basically, unless you're a very good skier, we can go up the mountain now also because of electricity. Let me remind you of that. Okay, so here is another example of this. People ask the following question. What happens with radiation that comes out from an electrode? This was a question that was asked in the beginning of the 1900s. This guy, Röntgen. Röntgen asked the question, what happens, he found actually by accident that some electrodes that he was putting a current to them emit this radiation. He was asking, what the hell is this? And he started studying this. Look, and here's the first X-ray picture. I'm told, and actually there's some debate about this, that this X-ray picture is the hand of his wife. Okay? Now there it is, this X-ray picture, the hand of his wife. Now imagine, here in a skiing place, this is a good one. When you go to the doctor, when you have this misfortune of being there, and I almost thought about this, you know, that I'll end up not giving this talk if I break my neck down the slopes there. The doctors before, to know what's inside your body, they had to cut it up. You don't have to do that now, courtesy of William Röntgen, who was a physicist, who got the Nobel Prize, the first Nobel Prize in physics in 1901. So this is a miracle. We can look inside the body of somebody without touching it. But not only that, this is a much bigger miracle than that. Look at this. See, this is his wife. His hand. See, that's the ring there, his wife's ring. This guy was able to convince his wife to put her hand under this thing. I have not been able to convince my wife of anything. She doesn't come into the lab even close to this, you know, much less to put her hand under anything that I have in the lab. Okay? So here's another question. Why different elements absorb radio frequencies? So you have these radio waves that go around. It turns out that different elements absorb them differently. This gave rise to something called nuclear magnetic resonance. This word was dropped because this was not a very popular word. Nuclear is no more, and it could be that the reason for this is, the Republicans will forgive me, is that because our president doesn't know how to pronounce that word also. Okay? that may be the origin of it, but probably not. But you know, so now it's called magnetic resonance imaging. There were 2 Nobel Prizes for them, the original people in physics. These were Bloch and Purcell and Lauterbur and Mansfield. And look, we can look inside your brain. We can look inside your head, look at your brain, and nowadays there is what is called functional MRI, where they can see you thinking. We can see you thinking. Okay, this also, if you're in a skiing place, if you have any problems with any soft tissue, they're going to put you under an MRI machine, courtesy of physicists. Not the medical doctors. They cash in. I have to wear this goddamn t-shirt, but they cash in the money. Okay? We invent these things, okay? We can see you thinking. This is like magic. So the electromagnetic radiation, we can see through things, we can extend our health, obviously. Okay, so here is a basic question that more closely related to what I do. Can one control the movement of an electron using an electric field? What does that mean? Can I take a bunch of electrons? So the electrons, for those of you guys that don't know, it's these little particles that have a negative electric charge. You put a battery to them, and can we do this? Can we put a battery in one way, and these electrons walk up, and then, so that I call electric field positive, then I take this, the battery, turn it around, you see those arrows point the other way, the electrons go down. Can we control that? And this gave rise to this invention, which was called sorry, TV guys, sorry, just a moment here. Little higher, okay. Okay, so this gave rise to this audion. Here it is an audion. It's a tube like this. What this is able to do is it's able to control the motion of those electrons. It's this very simple device. Basically consists of an emitter of electrons there in the middle, this red thing, and a collector of electrons, and something in between that controls the motion, the audion. This audion was the basis of radio communications. Was invented by this American scientist, Lee DeForest, okay? And this gave rise to communications that people now could communicate with the top of the Himalayas, okay? We could talk through the radio without having to have wires. Now the nanoscience. Now I'll tell you about the beginning of nanoscience. This is actually from the Sistine Chapel, just in case you guys think that there is some erotic meaning to this, okay? Okay, so this is culture. Okay, so here it is. You can ask the same question in a solid. You can ask the question, you take a solid material, and you can ask yourself, can I control the motion of those electrons in a solid material? So this is the question I have again. These little electrons here, they're walking around, they go inside a solid, like that brick wall. And can they go through, and can I control their motion? So that's a basic question that we scientists ask. Can one control the motion of an electron inside the material using an electric field? That's how we phrase it. And this gave rise to the most important invention of the 20th century. So I do the 19th century, the 20th century. Any guesses? Almost. No, it's the transistor. Yes, Andrew? You better have the right answer. No. A transistor, that's the one. See, he knew it. He's the one guy that knew it, okay? It's the transistor, okay? And that's how a transistor looks like. Why is that important? That gave rise, this was invented by Bardeen, Shockley, and Brittain in 1956 Nobel Prize. The reason is because this suddenly gave us the glimpse that we can make things very small. That we can make them much smaller. Now remember, before we used to have this. Now we have that, Shockley and Bardeen and Brittain invented this. Then what we did, we took 1 million of those and put them into this. So this is from a PDP 8, for those of you guys that are old enough to remember this. Then we took 1 million of those and put them into this. Okay? And then we took 1 million of these and we put them into this. Now this is, before I was coming here, I needed to show you a Pentium, so I went into one of my colleagues and I pulled this thing out, so he's trying to calculate now. So there's 1 million of these into this, and this gave rise to something that even I, 25 years ago, I would have said you're out of your mind if you think that this is going to happen. Because we can, not only that we can communicate with the radio, to any place in the world, but now we can have these computers where we can, if I would have told you 25 years ago that you will be able, 25 years from now, communicate with every library, buy tickets on the internet, communicate with your friends for free, they would have said, take this guy to the loony bin. Okay? So those of you that are old enough, like me, you would remember that. Nowadays it's normal. Nowadays it's normal. You sit on the computer and you do this. Even the smallest children, Andrew probably has 3 computers in home, right? How many do you have? Do you use a computer, Andrew?
One that doesn't work, it's my little laptop.
Okay. One that doesn't work. That's the problem. You see, here it is another example. This is where we blame the scientist. When the thing doesn't work, Andrew gets pissed off. Okay? So we are so accustomed that these things work all the time that they are accustomed. Okay, so here it is nanoscience. So here it is how small things are. So this is a bacteria, and there are small magnetic dots that I can make in my lab. Now, how small is this? I mean, it's very difficult to give you an intuition to how small it is. And what I'm going to do, I'm going to let you, a friend of mine, Adam Smith, explain it to you. So here it is the question that I will ask you. How small, how many atoms you can put in a hair, in just one strand of hair? Think about this question. I want the scientists to think about, give me a gut feeling about how many atoms there are in one strand of hair, but somehow a gut feeling. Suppose every atom is the size of a peanut. What's your gut feeling? How many peanuts you have there? Yeah. Doesn't matter, this long. Okay? It doesn't matter. Okay? One here, gut feeling of the scientist. Think about this problem, all you scientists here in the audience, but Adam will explain it to you.
Now where was I? Oh yeah. Remember our hair? It's a whopping 80,000 nanometers wide. So, how many atoms are in it? Let's see. I need something small.
Peanuts! Peanuts!
What the? Oh well. One, over here.
Got it.
Thanks. Hey, don't you own the Padres?
I do.
Why are you up here selling peanuts?
Well, you're buying, aren't you? We got to pay for the ballpark.
Maybe I should buy two. Hey, thanks. Perfect. If each atom were, say, the size of this peanut here, that would be enough peanuts to completely fill this ballpark. Now that is one heck of a bowl of peanuts. Whew. I'm gonna get thirsty. I wonder if that guy sells sodas too. Anyway, we could easily fill this entire stadium. And there would still be enough peanuts left over to fill every ballpark, every stadium, every sports arena, every ice rink, field house, and gymnasium on Earth 1,000 times over. And still, the particles that make up those atoms are even smaller, only thousandths the size of our average atom. And with all this, we're still only talking about the number of atoms in a single strand of hair. Even so, this tiny scale is real. As real as, well, baseball and everything else we know. So why are Ivan and people like him working with such tiny things? Because when things get small, Ivan and his friends can do things that can seem unreal. Things that can seem like magic.
Okay, so out of this came this very important, you see, I was giving this talk, the reason I made this movie, this is actually part of a movie that you can download it from the web if you want to see it, and the website was there, and if you want to know about it, or Google me and you'll find the movie. It's a 27-minute movie, so it's much more than this. But the reason I made this movie originally was because I was giving this talk many times, and I was asking always this question, how big is a strand of hair? And you can see what happened to my hair. I lost it, almost all of it, and so there is several people here apparently give the same talk as I give. Okay, right? And so, so I decided to have Adam do this for me. But and out of this became, one day my wife came home with this very important application, which was this thing here that I'm going to show you now. This is a Giovanni shampoo. You see, Giovanni, this is a real stuff. And none of this is made up, it's real. You see, this Giovanni shampoo, it's E equals minus mu dot B. I just want, for those of you guys that are scientists, what it says here, actually, you can't read very well. It says magnetite is a mineral that infuses positive energy. I just want to point out to the scientists, it says positive energy, it says a minus sign. Never mind that, but I mean, okay, and then, this is the positron effect. All this is nonsense, but some people buy this shampoo for some reason. You can see how flowing my hair came with this shampoo. I gave it to one of my colleagues, a professor at UCSD. You can see he also became very, he's also improved his looks with the Giovanni shampoo. Okay, so that's not what we are talking about, okay? We're talking about more serious things. So what's the point with when things get small? Because when things get small, you see there is some other equation. There's this equation called the Schrödinger equation that we use. And this equation has this other magic behind it, which is very difficult for me to show it to you. Because it's very difficult to show at this scale what happens when things are very, very small. Okay? So what happens when things are small? When things are very small, they're very different. That's the point. They're very different and they violate what your intuition tells you. Okay? So, what do I mean by that? They become sort of magical. Now, how small I'm talking about? I'm talking about as small as that guy was talking in there, nanometers always, and that's why this whole field is called the nano field, because a nanometer is something very small. Okay? And so, for instance, let me show you a magical thing that happens here, that Nana was very generous and got me this ball that, you're accustomed that if you take a ball and you bounce it, if Nana would give me a good ball, it bounces all the time. But one thing you're certainly accustomed to, that not only that it bounces, but this ball never goes to the floor below. It never goes under the stage. Never. And nobody would ever doubt that, right? If I tell you this ball will eventually go through this, they would say you're nuts. Well, I'll show you an example that is not the case. When things are small, that effect happens. That is called quantum mechanical tunneling. Things go through walls. The balls, if they're small enough, and you throw them enough times against the wall, they go through walls. They're like magic. That comes out of that equation that I showed you. So that's what they want. Now, look, in addition to that, the electrons turn. These electrons that have these charges, they turn. So they have what is called a spin. They are like little magnets. Okay, so what am I trying to show you here? What I'm trying to show you here is that typically in an electron with a negative charge that I showed you before goes through these walls, then it keeps memory of this charge. But when it spins around, like these electrons below here, which is indicated by that arrow there, they forget their spin. Okay? So this is a question that you can ask. Why and how these electrons forget the spin? That's a simple question that you can ask. That's what has been actually my research. So how can I not talk about this research? Actually, I started working on something called magnetic superlattices. So I published this paper in 1980. It was the most boring in some conference in Hawaii. I'm also not only a skier, but I'm also a scuba diver. So I immediately published this paper, gave it to the editors, and I went diving. Published this paper. I won't tell you, it's a very boring title. It's called Transport Problem, something that you really don't want to hear. But even Nostradamus, who many of you may believe in, couldn't have predicted what will come out of this and it will be useful. I went diving after I published this paper, and I got the following surprise out of this paper. I found a surprise, which what I said, well, I'll explain to you in just 1 second. Magnetoresistance shows anomalous behavior. What we said is that there is a 20% magnetoresistance. So the scientists will appreciate this. You may not appreciate this. You'll appreciate it in just 1 second. So we said this in this paper, and telling you, I went diving, which was the wrong thing to do, actually, at that moment. I should have continued working on this. And what this means, here it is. So I told you the spin memory is nanoscopic, so I can ask the basic question. Can I control the motion of a spin of an electron with a magnetic field inside the material? Same question that I asked before. And here it is the question. There's my electrons with a spin. They're going there, and can I control their motion by putting a magnet on it? That's what that boring paper was all about. So then after that, in 1987, some other guys who you see, I don't even want you to read this, published another paper in some other boring journal, for those of you that are experts at physical review letters, okay? Some crappy journal that there is around there. And they came up with the following conclusion, that if you have an electron with a spin that is spinning here in a material, and there's another one that is spinning there, they cannot communicate if they are far away, because the distance is too large. However, if you put a magnet on it, and you ask what is a structure like this would do, it won't do anything. The electrical resistance won't change. It will stay the same. However, if you have these two things very close together, so they are at a nano distance, they're very, very close together, then this electron can communicate with that electron. So they're shaking hands there. And then if you put a magnet on it, then there is a large change in the magnetoresistance, the electrical resistance of these materials. So the electrical resistance of these materials changes enormously. That is called now in the literature the giant magnetoresistance. And that thing, it's everywhere. These two guys, you see this guy how is he smiling? And you look at my face? This guy is smiling because he got the Nobel Prize this year. This is the Nobel Prize of this year. So if you wonder what the 2007, well, it's last year actually, but the 2007 is this thing. It's in every one of you guys are using it. You're using it in your read heads, in your computers, and it's right here in your read head. So if I can figure out how to make this thing work, it's right there. That's your read head, and it's inside there. Every single one of those computers that Andrew is using, or well, maybe in Andrew's case it's broke down, but in the other places that are using it, they work based on this principle. It's in this giant magnetoresistance, and these guys, luckily for them, they got the Nobel Prize in physics. You use it, therefore, and so you are using nanoscience right now, right at this moment. It's in your computer read head. It's in an iPod. It will be there on your telephones soon. Well, actually, they're selling telephones with that already. This came out of basic research. I told you I went diving. If I'd known then what I know now, I would have first invested. Indeed, the second thing, I wouldn't have gone diving. I would have gone to the lab, so I get the Nobel Prize. Well, I didn't know. That's the point. It's hard to predict. And this gave rise to applications such as the computer, the internet. It expands our brain. I can tell you, when you get to my age and you forget something, many times when I forget something, the first thing I do, I go Google it. Right? I Google things and I can, who was the person? I just go Google it. That's it. That's right there. Okay. So I will just finish in just 5 minutes. Is that okay? Okay, so let me show you another example of something that obviously has to give you a very important application. Suppose I take an electrical conductor and I have this, I ask myself, how do the electrons move inside that electrical conductor? They move like this. Okay, they move like this, you turned it off. No? They move like drunken people. Okay? So now you see, for us to get paid a high salary, we say the electron scattering gives a high electrical resistance. And so you guys that are not scientists don't understand what we're saying. All we said is that these electrons go around and they bounce around the walls. Now there are these materials, these new materials that were, well, not that new actually anymore, that do this. The sound doesn't work. Okay, again, let me just, you did something to the sound there that, yeah, well, okay, doesn't matter. Take a look at how those guys work there. Okay, they work together cooperatively. Yeah, okay, they work together, all of them. Instead of bouncing around, they work all together. So what we say, there is macroscopic coherence. These are the words the scientists use. But all we're saying is that those electrons there move together. They have macroscopic coherence, which gives zero resistance. And this obviously, if you think about it for just 1 instant, this obviously has to be useful. I mean, this is, the whole world should know about this. This is called a superconductor, these materials. And if you have superconductivity, you don't have electrical resistance. This clearly has to be useful. And there have been more Nobel Prizes in this field than any other field. All these guys got the Nobel Prize in this field. In different years for the discovery of it and for all God knows what. Lots of different things, okay? And for instance, in the 87, there were all kinds of things when there was some big revolution in this field and this thing appeared and they showed the superconducting for electrical energy systems, superconducting motors. They even floated a guy, a sumo wrestler, on top of a superconducting disc. Fantastic. We said we're wiring the future. The superconducting revolution was in every magazine, every place in the world. Okay, where is it? Nowhere. It's obvious that it should be useful, and it is not. Because it's hard to predict where it is useful. That's what I want. So I wanted to show you an example of exactly the opposite. So I worked on superconductivity. I thought this is useful. It's not. I mean, really, it's not. No, nothing is superconducting here. We don't use it. And it's obvious. So here are the major revolutions that I told you. The Audion gave rise to this wireless, which extended our ears. When we changed it 1 million times, we got new electronics, which extended our eyes. We made the integrated circuit, another Nobel Prize. It extended our hands. Now the microprocessor, it extended our brains. Where are we going next? Next is this revolution, the nano revolution. And I think that I'm going to stop at this moment, Nana, and we are going to ask, we're going to let you participate in this more instead of me telling you more and having you. Thank you.
Well, first thing I have issue with is this banana technology, because nana technology.
Oh, banana technology, right, exactly right.
More appropriate. So how this usually works for those of you who haven't been here is I hog all the questions at first, and then I let you share, in the experience. But
actually, I think there was a man right there that wanted to ask a question. Right?
Well, MRI, you talked about MRI. And MRI uses superconductivity all the time. They have to cool it with liquid.
Okay, here's a guy.
Temperature.
You got me.
And there's an entire
You got me. You got me.
MRI wouldn't work without contrast agents.
Yeah, but...
There's chemists in
Okay, let's not have this discussion here because, I have, as I say, people, some of my best sons are chemists. I have one of my 2 sons is a chemist. So, how can I be bad with a chemist? I mean, my son is a chemist. Okay.
It's just the chemistry of small systems.
Okay, oh, here's a, oh.
Well, this does bring me to my very first question, which is I did notice a serious bias in his talk about physicists reigning supreme.
We're used to it.
Well, physicists, we have this, I mean, let me put it this way. These talks that have to be given, I can't do it for everybody. I mean, so I kind of have to, you know, do what I can, and, you know, at my age, that's all you can do. So I was coming down the slopes there, you know, and I did whatever I could there, or no, you know, I used to do much better before, so.
One thing I'm curious about is, and one thing that you didn't touch on tonight is, there is a lot of criticism of nanotechnology and what it can unleash into the environment or into the human body. And there are certainly a lot of alarmists out there. Bill Joy was one of the first, I think, in 1998 or 1999, to talk about self-replicating robots. Michael Creighton has a book out about that. And I was just curious, of all these things that, of the various claims that are out there about the dangers, which one irks you the most that you think is absolute rubbish?
Well, I mean, you know, I guess people told me that when the train was invented, people didn't want the horses to be stopped because, you know, because you're going to move at a very high velocity and it's going to destroy your inner organs and things like this. All technology, of course, a train, if it collides against your SUV or against your car, you know what's going to do to it. Science and the developments that we have from technology are sometimes dangerous. You can make nuclear energy, and we could pretty much, you know, solve the energy crisis of the world with nuclear energy. We can make atom bombs out of it also. So this is the same. I mean, so it doesn't hurt me. It's just, I find that there's the same criticism. It's always, of course, you have to be careful. You have to watch out for dangers. Every technology has this problem, and so of course you have to do that. But that does not mean that you're going to stop the developments. I mean, so let's turn all the lights off. Let's stop all the ski lifts, and let's stop, you know, I don't know, where would you live here if you wouldn't have any technology available to you, okay?
The Ute Indian did not live here in the winter.
Okay, so that's what I'm saying. So at the end of the story is, of course, there is dangers to technology. There is these things for children that left. There is these holes in the wall, okay, that if you stick a paper clip into it, you know, you'll get zapped. Now, that's dangerous. That can kill you. Now, you know, are we going to plug all the holes in the wall? For those of you that don't know what I'm talking about, you know, I'm talking about electric plugs, okay, just in case. All right, I mean, so everything is dangerous.
Well, do you have any personal concerns about nanotechnology? Is there any spot that you think is particularly dangerous and that society or scientists should pay particular attention to and actually anticipate some problems that might arise?
Well, there is, of course, I mean, I presume that there is dangers if you make things, for instance, asbestosis, which is a well-known disease that comes from asbestos. So far as I understand, and I know very little about this, but so far as I understand, has to do with the fact that asbestos fibers are of the same size as the alveoli in your lungs, and so they're not neither smaller nor bigger, so they plug it up. Okay, so I presume that if you make nano-sized particles that somehow can go into your lungs or something and plug things up, it may be dangerous. So I presume I can invent scenarios by which I can kill you with some nanotechnology, okay? But it's like talking about a knife. I mean, a knife can be a very useful device, and it can kill you. Now, you know, the uses that you give it, so it is not that I'm a crazy defender completely of technology, but the technology properly used, and so of course you have to watch out for this. But there is people that go nuts with this thing of, you know, of criticizing technology and wanting to stop. Every time there's a technological revolution, there's a bunch of people that stand up and say, well, this is going to do this, you're going to have nanobots. There is this person that invented this thing, and I don't want to get into these, you know, arguments but, you know, they make up this story about nanobots, and there is these little guys that are going to get in your bloodstream and are going to kill you. That's what the bottom line is. I mean, you know, that actually is not real, incidentally. That is all science fiction. There is no such a thing.
So that irks
okay?
you.
Well, it doesn't hurt me because, I mean, I just find it, you know, I try to dispel that notion. That's basically what I'm trying to do, is to dispel that notion that everything is dangerous in life and you know, skiing. Okay, here, we're talking about skiing. Skiing can be extremely dangerous. Now, you know, luckily, in my 60 years, I never, but you can break your neck. And you can become paralyzed from the neck down. Now, okay, so here, stop skiing. I mean, everything can be dangerous if you give it the wrong use. That's what irks me, is where you try to blame something on something that actually improves our lives enormously, and you say, well, if you give it a wrong use, then you are going to die. Well, yes, I agree. But don't give it a wrong use.
Do you have a question?
Yes, carbon nanofibers have found some uses, especially in plastics. Which elements do you think will be the next ones to find some commercial uses?
Well, carbon, there is a talk about carbon, not only nanofibers, but carbon nowadays in the physics community, so if the chemists will forgive me, the big deal now is actually there is a claim that you can make one single sheet of carbon, of one single atomic sheet of carbon. They gave it a name, and that was brilliant, because as soon as you gave a name, it becomes very popular among scientists. It's called graphene. And presumably that has some very unusual electronic properties, very unusual. So that's possibly something that will give rise to some interesting applications, but I'm not really sure. There is a lot of talk about many of these organic materials that I'm here at a conference where people are taking organic materials, things that contain carbon, but they're not carbon nanofibers, but organic materials that have carbon and hydrogen, macromolecules, for instance, DNA, and they put it in contact with not inorganic materials like gold or one of these elements here in the periodic table, okay? And out of making these things, putting them in contact, they can come up with applications. Some people are thinking of drug deliveries, special drug deliveries, ways of delivering drug targeted to a point. Some people are thinking of it as using it as sensors. There is, infinite. The human imagination is infinite in this. But that perhaps will give rise to. But the one thing that it is, you have to realize about science. Science is incremental. Science is not. A lot of people believe that there is something happened and then boom, we get all this. It's not like that. It's even the transistor. There was the Audion, as I told you before that, and there were lots of people that were working on this. So it's kind of slowly pacing. So it's not like there's suddenly something coming out.
How does, because you are so interested in science communication, and I strongly recommend his film, it is truly one of the best science films that I have ever seen, and I'm interested in that kind of thing, and I'm sure you guys are too, otherwise you wouldn't be here, but it's funny, it's engaging, it's wonderful. When things get small, just like you said, Google him and watch it. It's completely entertaining. But there are very few scientists, I don't know how many of you here, who dedicate a lot of time to science communication as Ivan does. And it used to be called popularizing science. And a lot of scientists get criticism for dumbing down or that type of thing. And I think, I obviously am very interested in the field of science communication and do believe it's important. But how can a lay person begin to tell the difference between nanoscience and nanoscience fiction?
You got me on that one. It's very difficult. I can honestly tell you that actually I'm in the process of trying to make one of my next movies. Actually, I have a whole series in mind, When Things Get Something. In my next movie, actually, believe it or not, that I was in communication already with the chemistry division. This I'm telling it to the scientists about. That's the other reason that I came to this meeting. Because my next movie, I wanted to do it when things get slimy. And that was going to be about polymers and macromolecules and things like that, okay? Precisely to address some question like that you're asking. To address, because everything I told you here is scientifically correct. I haven't told you anything except the jokes that I hope you guys got it, that it was a joke. It wasn't, the thing about my hair and things like this. This gentleman here is smiling. Right? Okay, I hope you got it, that it was, and everything else is scientifically correct. So I will make a movie about this, about what we are talking about. I hope, if I can get the funding for it, about movie, when things get slimy. Now,
what's the punchline of that?
Well, I mean, I'm not exactly sure because the script is not fully written, but the only difference between the last movie that I made and this one this movie that I made doesn't really quite have a storyline to it. And I want to make it, the next movie is going to be a spy movie, or kind of in the style of Maxwell Smart, kind of. So that's what I'm trying to get funding for it. But I mean, what I want to do to show you is that the slimy things are actually useful. That's what basically the bottom line is, that it's interesting and it's useful somehow.
One thing I learned in this conference, mostly I'm just a coffee girl when the scientists are around, but so I eavesdrop on what they say, and typically you can't understand anything because the language is so specific, but wiggle That is a scientific word. And they wiggle over there. And they have machines called wigglers. Does anybody have any questions? Yes?
I have the disadvantage of being a scientist, but there's one, yeah, I'm arrogant enough to be a physicist. I hope not, given my mentor. You can try Wikipedia. If you want to tell the difference between science and science fiction, if you bought it in the bookstore and it was in the fiction category, like Michael Crichton is, then a lot of that, I mean, his talent is combining good science with a good story. But if you want to try to tell those apart, try Wikipedia. It's actually pretty good, okay? If you have a question, look there.
Well, Wikipedia is sometimes dangerous. I mean, okay, so now you're going to see what scientists do. We criticize each other instantaneously, okay? So he says something, I'll say, no, it's wrong. Okay, that's what we usually do. But I think that with Wikipedia, you have to sometimes watch out, because sometimes, anybody can put things in there, and then sometimes it can go the wrong way. But it's very difficult. I mean, I think that is a fair statement. It's very difficult for a layperson to tell what is. I think I would say this. Let me just come up with kind of an instantaneous answer. I would say this. If you look at a legitimate scientist from a legitimate place telling you something, you probably can bet on it that 90% of the time it's correct and it is legitimate science. And 10% of the time it won't be, because it's either wrong or he is misleading you in purpose for some reason or something. But I would say that's probably a good bet.
Well,
okay? Now we are human, and we get corrupted also. So so I'm not going to say that we're perfect, but I think that's a good bet.
Well, you talked earlier about how there's a general confusion between science and technology. And I would offer that a lot of that confusion stems from the media, because if they ever print an article that's about science, they inevitably talk about its promises. And those promises are the sort of thing that you have spent a lot of time today saying are not predictable.
Right, and so that's basically the issue, that it is not predictable, and then journalists, now, I don't blame them, because journalists have to have a headline.
Yeah.
And they have to have a headline. They have to put up a headline, and a headline you can only put up, we have cured AIDS. That's a headline.
Yeah.
If you say, well, we've done some research and there's some macromolecules, and I can tell you, I can confess to you the truth. I don't understand 75% of what these guys are talking either. Okay? And they can vouch for it, because they ask questions. They say, what the hell is this guy asking? So I don't understand it myself. So the science is so polarized nowadays that it's very hard to understand what another scientist is talking about. So,
So is it, getting back to science communication, whose job is it? I mean, I'm a layperson who likes to communicate science because I find it interesting, and I feared science most of my whole life. And then I finally figured out that it was kind of an interesting thing. Is it the job of scientists to take away their time from their research to do what you do? Because journalists don't necessarily, or people like me don't necessarily give it a fair portrayal.
Okay, for that one I have an answer, a definite answer.
What?
I think you're right. There is this situation in which scientists try to explain science, and usually it becomes extremely tedious, because we don't want to say anything that is mildly incorrect. So everything is very qualified and make sure that everything is correct. And then it becomes, everybody goes like this. Okay? And then the journalists take it that on headlines. Now, I think that the obvious solution, there is an obvious solution to that, and my movie actually arose as an obvious solution. The obvious solution is to have a partnership. People that know how to communicate. So I actually have a partner. So this movie is not that I made a movie. I'm not crazy enough to try to make a movie. This movie, incidentally, won 5 Emmys. So it's not like just, it's an okay movie. And it's not like I'm crazy enough to think that I can make movies. I partnered with a producer, a science producer from a TV station who knows how to communicate, who knows what the pitfalls are, so who knows where you can go wrong. And we wrote the script together, and in fact, we kind of did it on a shoestring, so that's why. But I think that's the answer to your question. You have to have a partnership. You have to have a partnership between a scientist and a communicator, and they have to go together, but they have to go together as equals. And I think what happens is that many times what happens is either the scientific partner dominates it, and then he wants to put all these caveats and all these qualifications and is not willing to let go, or the communicator dominates and says, well, you don't know how to communicate, so shut up and let me do it. And this happens. I've seen this happen in both of these things, and I think that somehow you have to have a real partnership, but both of them are equal, and they're willing to let go one, and the other one is willing to let go and really partner. That's the answer to your question. I definitely think that that's...
And I have one quick question, and then that's where I'll open it up. So why, I mean, I have a lot of my own answers on why I believe that science communications is important. Why do you believe it's important?
Well, I think there's at least two reasons, and we were today in the lift. We talked about it at least 3 times up the lift, about exactly this question. I think one reason is simply it's our obligation. We are actually pretty much working, most of us that are scientists, not technologists, we're working out of the public, the public is funding us. So I think it's my obligation. I mean, you guys are paying taxes, and my salary is paid out of that. And my research is paid out of that in some form or another. I mean, it's not, but at the end, it becomes out of taxes. So that's my obligation. I mean, I have an obligation. But the second thing is that I believe that we're losing a large portion of our population because they don't know what the hell the science is all about, and then they are misled, and then there is all these problems, and then we complain. And I had conversations also about this with scientists, and the ones that I had conversations with them know it, that they say, well, the public doesn't understand us. They don't understand us because we don't explain it to them. So that's the reason. And so this is preaching to my scientist friends. You have to do it and not to complain about it. There's nothing, it doesn't do any good to complain about it. It doesn't help anything. So I figured, okay, I'll do whatever I can, and if people don't like it, tough luck. I mean, what can I do? But that's what I think it is. It's our obligation, and it helps us. I mean, it's in our own best interest. People are going to realize science is, somebody once, Kroto, I heard a talk by Harold Kroto, who is the man who got the Nobel Prize in chemistry for inventing buckyballs.
Chemist.
Yeah, chemist, Dr. Chemist. And he said the following, is that if you go, there's a place in Spain where they have these people go there to pray and to get this holy water there. And the claim is that there were 4 million people, and I actually wanted to include it in this talk, but finally didn't send me the PowerPoints. That the 4 million people went there, and even by the acceptance of people that believe in this, there are about 50 people that got cured. Even if you take it, okay, so 4 million, out of 4 million, 50 people got cured. Now, he shows a picture of a complicated molecule, and he says, see this molecule? This molecule will cure you every time. It's called penicillin. Now, if it doesn't cure you, you complain. You go and yell at the doctor, yell at the chemist or whatever, yell at the physicist, okay, yell at somebody, because it doesn't cure you every time, and it's a miracle. That drug is a miracle. It's much bigger miracle than whatever miracle you have in that place in Spain with the holy water. I'm telling you, just simple numbers. Penicillin cures you every time. That thing cures you 50 times, I'll grant it to you, out of 4 million. Okay? Andrew, that was sitting there on the floor, was all upset because his computer didn't work. That's my fault because, the computer should work all the time. So that's the difference between science and these magical things. These magical things that are magical, they don't work. Face it. And if they work once in every, And the TV, look at the TV. It's full of these people that are selling you things. I mean, literally. That you send them money. No scientist does this, goes there. Although, I have to tell you something extremely funny that happened to me. Yesterday, I got an email. Now, this a scientist will appreciate this. From a friend of mine who told me the first time in his life that he has seen a scientist really trying to sell his work. Meaning, some guy sent out a paper and he said, if you want to publish this paper on your own name, send me $1,000. You can publish it on your own name, I swear to God. So the scientists will appreciate the humor of this. So for $1,000, I can give you the name of the person, and you can have one more paper attached to your life, okay? So even we get corrupted.
Any questions? Yes.
Just kind of a general philosophical comment. I mean, what you did, I think, is wonderful, and we're about the same age. I can remember Mr. Wizard. And I can remember PSSA physics that I took and all of that. And it's great to have this partnership between the journalists and the scientists. But are we really reaching people? There's a really interesting report from Washington called "Rising Above the Gathering Storm," and I think it's a really grim and a really pessimistic prediction of what this economy is going to do, our ability to manufacture things, our ability to innovate. And I just worry sometimes that we're pissing in the ocean.
No,
major problems.
I completely, totally, and absolutely agree with you. I think we're not reaching the people. But I think we're not reaching the people because we're doing it the wrong way. And I think that the key is the following. I told you when I started this talk, if you people that are not scientists walk away from here thinking science is one of these things that some people find it interesting, I don't care about it, but I know that the totality of it will lead to something useful, and it's a very worthwhile enterprise that makes my life better. If you walk away with that, that is and that, I think, is the sufficient message that we have to give. I don't think that in particularly you have to know that electrons have a spin and you can control it and GMR and these kind of things. I think that that is, that's my research. I don't think that's a secondary thing. But I don't think we're reaching people, and I tell you why. I don't think we're reaching people because we try to educate them. And I think that what we should try to do is to entertain them. The science education, what is called science education should not be called science education, should be called science entertainment, because the large majority of people do not want to be educated. Okay? They don't. They have their own things. They do their own things. They don't want to. I know I don't want to be educated, actually, about things. I want to be entertained sometimes. And if through entertainment somehow we can carry this message, and maybe they learn something, maybe they won't. I don't think learning something specific is that important. So that's my answer to your question. And as scientists, we always disagree on pretty much everything. I can tell you this one thing, that all the places that fund this kind of work, let me put it a different way. I can tell you this, that it is much easier to get money to do research, at least for me, than to do this kind of things. It's much easier. People pay a lot of lip service to this kind of scientists. The National Science Foundation, the Department of Energy, try to get money to do this. This movie cost $450,000 cost. I got $70,000 from the National Science Foundation. The rest of it I raised it on my own. And I will tell you this, for my second movie, I'm having a hell of a time. Because some people that give money, they told me they find this movie too elementary. My wife found this movie too difficult to understand. I'm not joking. She told me, you should take these parts out of, there's certain parts in the movie, which I agree with her, kind of, but I don't have $20,000 to do that, re-scripting the movie. It costs $20,000. And she told me, it's too complicated, take this thing out, it's just getting you off track. Okay? So the problem is that there is no money to do this, and that's what I think, and that's what I'm trying to somehow improve on and complain and go and try to do, and I do whatever I can. But I think that if all of us scientists would do, here it is, somebody asked me today in the skill lift, so I had an idea, what should I do? And I said to him, you know what you should do? I have the answer to that also. Do whatever you feel comfortable with. That's what I think is the answer. Mm-hmm. If we all scientists, we do what we feel comfortable with talking to the public. If all you feel comfortable is talking on a one-to-one to a person outside there, talk to them. Talk to them and try to convince them that this is right. If you feel comfortable staying in a stage and talking to somebody and being on TV, do that. If you feel like you want to go on the comedy tour, go do that. Do whatever you feel comfortable, but we don't do it. Because it's very hard, and so people say, oh, the hell with it, I can get more money to do science. That's the problem.
Do you think scientists are actually beginning to take a little bit more of an activist role? I mean, traditionally science is objective, science is apolitical, but one thing that I've noticed in this, working with TSRC for 5 years, is that more of the scientists are beginning to give talks about issues like climate change or arsenic in the drinking water. And some of those scientists are actually not only involved in identifying and doing the research to understand why, take this example of arsenic in the drinking water of Bangladesh and Cambodia, but then go to the point of, while they're in those countries, work with GMOs to create the filters that will clean that drinking water that are culturally appropriate and cheap to manufacture out of existing waste products. I mean, just phenomenal solutions, kind of identifying the problem. Is some movement where scientists are beginning to say, we don't have time to be so partial and
that's when all the scientists banded together, and it was based on a letter that some scientists wrote to Roosevelt, and they banded together and said, we got to solve this problem. And they solved it, and I can tell you another secret. We live out of that. We scientists live out of that, because we saved, not only, we saved the world. We saved the world, basically, in the Second World War, scientists. And that happened also in the First World War. People don't know about many of the things that were invented by science. So I don't think it's a new phenomenon. Scientists kind of get involved, but somehow it looks more, you know more about this now. So I think that there is much more science going on now also. I mean, like, the normative science now. And the world is much more scientific. I mean, everything, if you look here in this room, and everybody here uses a computer. I mean, it's amazing. I mean, telling you, 30 years ago, if I would have shown you.
Does anybody else have a question?
Is there anybody from the public
You
that
I'd rather hear the non-scientists, actually.
Right, exactly. That's
There you go.
no. Well,
Aren't
he-
they hard on each other? God.
So
Go ahead.
I like the idea of partnerships, and I have a proposal that scientists, like any good citizen in a church community, make a tithe of 1% of their time. What's that, 3 days a year? And they partner with maybe a writer or somebody else that they know that can communicate a little bit, and they do something. And one thing that would be easy to do would be to edit an article on Wikipedia. Because actually, I use Wikipedia a lot. I actually use Wikipedia as a physicist to learn physics. And I use it to learn about cancer when someone in my family has cancer. Okay? And I use it to learn about how the solar system works when my 7-year-old wants to know how I mean, I need to know before she does, right? Or at least we do it together.
Yeah, but what happens when somebody comes and corrects your article that you spent 3 days of your time writing it for Wikipedia, and some other guy who didn't spend any time will go back and rewrite it?
You help write the article. That's okay.
Yeah.
So just to be a scientist disagreeing, we run a program for mid-schools, elementary schools, and high schools to do little solar cars and fuel cell cars and things like that. And our experience is that the way you get somebody connected to science is you get them to participate in something. And we've done this long enough that we are now seeing scientists come out of graduate school that got their inspiration racing a little solar car. And I think you can do Wikipedia, but I think you really have to get hands-on, and you have to get people involved in a really connected way.
And now to show you how scientists really look, I would disagree with both of you. I think that you should do what you want to do, and he should do what he wants to do, and both of those things are very important. Because he is talking about just educating the general public. You're talking about getting some guys, some suckers out of this who are going to go working as scientists. So these are for different audiences. But I'd say that you should do what you feel comfortable. He should do what he feels comfortable. And I should do what I feel comfortable. And then hopefully we're going to transmit something to somebody.
But you're all saying the same thing, which is that scientists do need to get out and interact with the public and communicate science in a way that's one can receive, whether it's
We
a kid
definitely, I think we all agree. The only issue is, at the end of the story, I hate to be crass, but at the end of the story, we can all agree in this, everybody has to be, but at the end of the story, the whole thing reduces, unfortunately, to money.
Yeah.
Okay, because these people will not be able to do this car, whatever they do with this solar car, unless they have money to do it, and that costs money. And even he, doing it, the Wikipedia thing, he can only do it because he's a scientist and nobody knows what he's doing, okay? So he can take off 3 days to do the Wikipedia thing, okay? All right? Is that true? No, that nobody really knows how much time you
And in the afternoons, I ski.
Yeah, okay, right. Exactly, in the afternoons you ski, so, yeah.
Questions? Yes, Eric.
I was wondering, does nanoscience have any relationship with neuroscience on a small level? And if so, is there any communication things that you might broaden up, like just the eyeglasses and the t-shirt, and kind of changing those elements in our mind?
Can you repeat the question?
Yeah, so he's asking whether there is any connection between nanoscience and neuroscience. And I think that definitely, I can tell you where a physicist does help in this neuroscience. In neuroscience is, basically looking, that's what neuroscientists do. I know about as much about neuroscience as you do, basically. I shouldn't say that. I probably know less than what you do because I know nothing. But I hear, and so what do neuroscientists do? They look at electrical signals in where neurons or the brain or somewhere they communicate, okay? That's where at least we physicists can come in there because we know how to measure small electrical signals and how to. So there is a lot of that kind of thing going on, definitely. So in my own department, in my own university, there's departments that are, and that's nano, because you have to be able to stick, imagine the small little, I showed you the size of, which are very fast, but the size of a bacteria, it's very small. And then you want to be able to stick in there a needle that is tiny, that it doesn't disturb the cell very much. You don't want it to disturb it, because then what the hell are you studying? And stick it in there and measure the electrical signal of that. So now that's where, you know, we can really do. I mean, so doing that, and it's very done in a very coarse way nowadays, and I'm not sure, I mean, I guess they claim that it doesn't affect the cells, but I'm sure that, you know, that's where it will. So that's a good example, for instance, where probably there will be major development.
We have a question in the back.
Yeah, just hopefully a quick clarification question. Where do you see the borders between nanoscience and quantum mechanics?
Okay.
How many scales of difference are there between the two?
Okay, the question is, what is the difference between nanoscience and quantum mechanics? I would say probably there is no difference between nanoscience and what happens in quantum mechanics is a theory that helps you understand these small structures that I was talking about. Now, what the difference is between what ordinarily we understand, all these atoms, we understand them very well. We basically have a very good grasp of what they do, how they do it, and everything. That's all quantum mechanics. What happens is that when you make things, when you put together, let's say, 1 million of these together, even knowing that one of them obeys the Schrödinger equation and 10 of them obeys the Schrödinger equation, 1 million of them do something somehow different. That is what is called an emergent property. That's what he made up, this word. And that's where, okay, so there is not a well-defined, length scale, but somewhere there where you have 100,000, I don't know, 10,000 of these particles together, that they somehow, when they become very complex, they do things differently that we cannot predict by actually writing down and starting in a reductionist approach, starting from the simplest and try to build it up. And that's what kind of nanoscience is look at these emergent properties. That's at least my interpretation, and I'm sure that pretty much everybody here that is a scientist will say, oh, that's wrong, it's something else. But that's what I think, perhaps most of us would agree to this, that it is. So it's not like you can take, for instance, the property of copper, let's say. You know what copper does, that tube, and you can kind of say, well, I'll make it smaller and smaller, and it's going to do this and this and this, and you slowly predict what a small thing. At some length scale of the order of, say, 100 or 1,000 nanometers, things become different. For instance, let me give you an example. Gold. Gold, everybody knows. You give your girlfriend gold rings because it's forever, right? It doesn't tarnish. It's non-reactive. It turns out that there's people that claim that when you make gold very, very small, it becomes very reactive, chemically reactive. So, why is that? It's very difficult. People have a very hard time with that one. I mean, there's people that explain it, but so I don't know if I answered the question. Did I answer the question?
And I have one last question, which is, there was a group of chemists here a few years ago, and John Forkas gave a talk on nanotechnology. I don't know if you know him. But the chemists in the group were saying that nanotechnology is just a new name for chemistry. I was wondering.
Well, in some sense you can say that. Okay, so what happens is that there is the president of the United States, Clinton. I actually use sometimes quotation from Clinton because Clinton actually said very well when he set up the nanotechnology initiative. He said, this is going to be research and it's going to take 20 years to come to any applications. That's what Clinton said. I have the quotation there. Okay, so everybody now tries to latch onto this word because there's money in it. Okay, so now we scientists are corruptible also, so there's money. So why do they say that nanotechnology is another word for chemistry? Because the type of molecules that we are dealing here at this conference are at the nanoscale. So you say, well, okay, that's nanotechnology. I think that is a wrong kind of a definition. I think that my definition in some ways is if a molecule does something unpredictable at some length scale, if you can actually simply calculate it and then say, okay, this is what it's doing in one atom, and then put another and another, and you can simply just calculate it, that is not nanotechnology. I think nanotechnology is something that suddenly, for some reason, something very unusual happens, and that unusual thing maybe requires a new way of thinking, that's what I think, but it's legitimate to say that nanotechnology because it works at the nanoscale and things are nano,
So, getting back to Dan's question, is nanotechnology actually going to unleash the break or fill the break between what is quantum and what is macro? Is it going to finally give, because that seems to be what you're talking about.
I think that is the point. I think in some way. So there is, for instance, let me give you another example. There's this thing, an example, quantum computing.
Yeah.
You might have
we
heard
had a
about
talk
this.
on that last
Okay, so quantum computing is one of these strange behaviors that occur at the sort of macroscopic scale, but not very macroscopic scale. And presumably it's useful to make, and God knows whether that will work or it won't work, but that's probably going to be a fantastic if it works. It's certainly used nowadays for cryptography. So quantum communication is used nowadays for cryptography, so there is uses already of this, okay? But it's hard to predict, and probably it won't work. I mean, it's easy to bet that something won't work. It usually doesn't, okay? But yeah, I think that's the way to put it, is you want to bridge the macro world with this very small world, and that bridging part in it is different somehow.
Yeah.
And we hope, actually, I hope it's different, because if it's just extremely, I can at the end put it in a computer, it becomes extremely boring, and I don't want to do that. I'll do something else. So I'm really hoping that it is not, just a simple extension.
So I think his message is basically that the work of most scientists is absolutely useless, and we're glad you guys come here all summer and year after year. And thank you, everybody, for coming, and thank you for your donations. And we will have another town talk on March 25th. There's another group of scientists coming into town. We don't quite have the title yet, but look forward if you're here. And then starting late June through the end of August, we'll have a town talk every Tuesday, mostly here. And Sancha has the slip of paper. Oh, we have to pull. Oh, Gina. Who wins the pinhead hat? Thank you very much to the Town of Mountain Village Homeowners Association. And like Gina was telling you all, we're doing this because our funding depends upon their getting their statistics. So, Linda Farmer. Okay. And let's give Ivan a big round of applause. Thank you so much.